Hello, it's me again, Jane Berry. Well, here we are at PCB design. We did some simulation in the front end and we did some organization. And now we get to the back end design, to the physical PCB design. Of course, we've got to realize what we planned in the front end and compare those simulations once we have all the physical stuff in place. But that's not the end of it. Those same ideas we used in the front end of reusing working hardware still apply here, and they apply in some different ways, like reusing placements, reusing routing. So let's get on with the physical design.
On the schematic, you've chosen the components and made connections. When you get to physical design, those drawn lines become conductors. And the signals those conductors carry are affected not just by those conductors themselves, but by everything that surrounds them, and even by signals on other conductors. Many recent PCBs carry a mix of digital, analog, and sometimes RF as well. Like this Internet of Things board, with its analog sensors, analog to digital converter, and satellite tracking antenna. Here, for instance, once the analog components in the A to D converter have been grouped, we draw a polygon using template areas. That carries the analog ground return. So even if we move the components around a little in that area or add some vias and routes, the template area will adapt automatically. Before we start to lay out new hardware, it's worth remembering that nothing beats working hardware. So if we've already laid out one USB channel, why lay it out again? We can just copy the placement from one channel to another. OK, back to that DDR4 memory bus we saw in the front end. Address command and control is going to be routed from the controller to each SD-RAM in turn. Copy placement will be useful here too to get the even spacing we need to meet the JEDEC specification. Now the ball-out patterns on these devices are designed to help you get a neat flow of routing, and usually you do that with trunk routing, but of course you don't always have the luxury of this much space to do it. With a bus like this, it's best to start by constraining the topology. This is the DDR4 clock that we saw in the front end. And we can add constraints directly from application notes onto these templates. And then after we apply these templates to real signals, we can check that the placement and routing achieves what we want. Like these SD-RAM to SD-RAM route lengths. There's much less scope for pin swapping on SD-RAMs than with earlier technologies, because of the need for speed and because buses are multi-purposed. But depending on your configuration, you can still often, for instance, swap entire byte lanes. And many controllers, like this one, allow ball-out reconfiguration to facilitate easier routing. So we get the buses routed. Here are the address command and control far-end termination resistors right under the file on SD-RAM, and the termination resistor capacitor network for the DDR4 clock. Signals like this DDR4 clock have to make intricate journeys, and it only takes one thing to be wrong for them to underperform or not perform properly at all. Let's extract an electrical equivalent circuit, a scenario for that clock, just as we did in the front end. You can see that although the basic topology is the same, the picture is a lot more intricate, because now we have the real routing and all the subtle changes that occur along the way. Well, back in the front end, those connections were still just drawn lines and we hadn't made them into metal. So we know what the results look like when we simulated in the front end, and the simulation tools are identical here. So after extracting the circuit in the back end, we assigned the same simulation models as we did there. We can see what it looks like now we've extracted a scenario from the physical design. And so far as the differential waveform's concerned, that doesn't look bad at all. And now we can check the eye pattern with all that physical stuff in place and compare it with what we had at the front end, more thoroughly and in more detail than what I've done here. While I'm here, I'll mention the analysis results viewer. This is exactly the same view you get in the front end, and you can filter the view to see exactly what you want. You can look at drivers, receivers, single-ended waveforms, differential waveforms, current waveforms, and so on, and you can set up a load of measurements, like you can look at overshoot, undershoot, and settled levels and all that kind of thing. It's very highly configurable. And the real beauty of all this is being able to see the scenarios from the front end and the physical design, and all of their waveforms and results like eye patterns together in exactly the same way, and so that it can compare them. Now, when I extracted the scenario for the clock differential pair, the only coupling I included was between the two sides of the pair, but you can include as much coupling as you like, and to do that you can specify everything you need in the extraction options. You can also simulate more subtle effects like passing over a gap in a ground plane, because doing that can cause an impedance discontinuity, and that can cause a glitch in the signal. However careful we are during PCB design, there's an awful lot to be careful about. For instance, it's all too easy to accidentally jog one bit like this bank address bit so that it overlaps row address strobe on another layer. That's going to give a lot of crosstalk. So setting up the extraction options so that we pick up coupling both on the same layer and between different layers means we can extract a scenario with all that included. And here's the coupling we introduced between layers with our slightly careless route. So I've breezed right through physical design there, and when I do that, some questions usually arise. I said that you can compare scenarios and waveforms between different sets of design data, and even between different users provided you have access. So how exactly do you do that? Well, the answer's a bit boring. It's file open, because there's no difference from front to back or with any other design that anyone shares with you. Now, I've shown simulation after extraction into scenarios, and maybe that seems a bit of a hassle. But you can simulate directly without going through scenarios at all. It's exactly the same, except without the editable equivalent circuit that you get in a scenario. So finally, how easy is it to play around with different topologies, see how they perform, and what other facilities are there in Electrical Editor that I haven't shown? Well, let's see. Just extract an address command bit and play around with a few topologies. What if I make it a daisy chain, or what if I switch off the right leveling and make it an H tree? Whatever I choose, I can do all kinds of simulation I can do anywhere else, and some of these I haven't even shown yet. You can simulate time domain waveforms, you can do a TDR time domain reflectometer analysis, you can generate eye patterns, you can parameter sweep passive components and even transmission lines to optimize the high-speed behavior. And you can extract an S-parameter model of your topology that you can use in analysis elsewhere.
Well, we've reached the end of PCB design. It's all routed, it's all placed. We've done those simulations and they look like the simulations in the front end. So we're finished? Well, that kind of depends. I mean, is this a fairly standard design? Or have we maybe been pushing the envelope? Do we maybe want to do some power integrity analysis? Probably, because one little mistake there could mean that the power's not getting through properly, and even if the DC gets through, well, there might be hot spots in the AC, there might be high impedance areas near components and so on. So if you push the envelope, you may need to push on a bit further to get absolute confidence. I'm Jane Berry. Goodbye for now.